So today is Wednesday, November 2nd. Chapter 6 assignments are due tonight. As such, we'll open the floor up shortly for everyone to ask questions about that. There's a couple of things about it that I specifically want to mention. A student brought up a rounding error to my attention that I want to address. Main thing that I want to spend time on today is beginning into chapters 7 and 8 together. This section we're coming up on is about rotation, and so as we begin it, we're going to define the terms that we're going to be using to describe rotational motion. Kind of going back to, in the beginning of the class, how we defined the terms we use to describe normal motion. And then we'll be using them over the next couple of weeks as we look at more types of rotational motion. I'll open the floor up to questions from you guys in a second. First, I want to glance at homework question number 6 because it was brought to my attention that part B has some very weird rounding issues about it. This is an inelastic collision between two vehicles. Part A, you should analyze the momentum. I think I still got that underneath. Part A, you should analyze the momentum in the system, compare initial to final. You do know the final velocity of the car, so the only unknown left to solve for is the final velocity of the truck. And that's what part A is asking. And you need the answer for part A to be able to solve for part B, which asks how much mechanical energy is lost in the collision. You should compare the initial KE sum of both vehicles to the final KE sum of both vehicles to see how much energy is missing on the final side. Now, what's a little bit weird about part B is the degree to which you round the velocity that you got in part A can pretty massively affect your answer. A student emailed in and reported they were having some issues with the question, and just for some context, the answer they got for part A was 21.05. That 0.05 is a very small part of the answer. So when they carried that answer into the second part, they just didn't say it. They just put 21 in their calculator because the 0.05 is very small and it could reasonably be rounded off either due to rounding or sig figs. But when they did that, their answer doubled from what it was supposed to be. Rather than if they actually included that extra 0.05, then the answer suddenly became about half as small. That's a pretty extreme difference for rounding off a digit to the hundredths place. And I don't have a very good explanation for why that is, other than these are very large objects and very small changes in their velocity do have a pretty big effect on their energy levels, especially when the velocity term is squared like it is in the kinetic energy formula. But even then, even if when I was working the question for myself and trying to keep in as many digits as possible to keep the answer as accurate as possible, I couldn't quite get the answer that WebAssign was expecting. It's as if it's rounding in a specific way or in a specific place, and it's insisting that you have to do the same thing without actually telling you where you need to round, or to what extent. Because even in part A it says round to 3 decimal places, but that still wasn't enough for me to get the answer at once. So between the percentage tolerance on the answer that it has as part of the program and me not being able to see the code for where the answer is coming from, it's likely that even if you do everything right, like completely to the extent that I'd say you didn't do anything wrong, WebAssign will probably still fight you on this one. What I'm going to do is I'm able to adjust the percentage tolerance on an answer. So like I can change it to where as long as you input a number that's within 10%, it'll count it correct. And using this as an example, within 10% could range anywhere from 97,000 to like 8,000. So I'm going to try to adjust that tolerance to increase a wider variety of answers, since I'm fairly certain no one's answer is going to be exact, because I couldn't even get it to work right. And what I'm going to ask for you guys to do is, one, whatever you get for A, try to carry as many digits as possible into B. And if it's still fighting you on that answer, let me know. I will make sure you get your points. It's just one of the weaknesses of using an automated program sometimes. Does that help anyone who may or may not have been working on this one so far? All right. Any other questions about this particular homework assignment for right now?
Did you go through how to do question 7, part B and C?
7, B, and C. All right. So 7, you do have to do these in a particular order because this is directly before and after cause and effect for each one. Just to briefly review, part A, 2 objects begin at a certain half on either side of the half pipe, and they will, at a certain height on either side of the half pipe. They will descend, their GPE turns into KE, and that will determine the velocity at which they will approach each other in the flat middle section. So for part A, transform GPE into KE, and that will tell you the velocities they approach each other at. Part B asks you to take those velocities and then examine what happens to these 2 objects if they have an elastic collision there in the middle. I'm actually roll this back up. Right on this one too. The question does say, that these objects are going to have an elastic collision. That tells us a few things about how we can treat that collision. 1, we know that momentum will be conserved in it, but 2, it means that KE will also be conserved, and that that third formula that we talked about that applies for 2 object, 1-dimensional elastic collisions also can be used to analyze the velocities of the objects involved. Now, in the example we did on Monday about the 2 vehicles colliding, we had to ultimately use 2 of these 3 equations as starting points to perform 2 equations, 2 unknowns, because we didn't know either object's final velocity, and that meant that no matter which equation we used, we would end up with 2 unknowns in it. So analyzing momentum, if you do part A first, you would know their initial velocities. You can figure out the system's momentum. Afterwards, though, you don't know either of their velocities, so you can't solve for either of them yet. This is why one would have to utilize an additional formula. And I'd recommend, as I did on Monday, the third formula listed from that slide. Using these 2 formulas in conjunction with each other, as we did on Monday, to perform 2 equations, 2 unknowns. It'll work exactly the same way as it did on Monday. It's just you change out which numbers you plug in for mass and initial velocity. Using these 2 formulas in conjunction with each other for 2 equations, 2 unknowns should let you solve for those 2 final velocities. Just to give everyone a sense of scale, their initial velocities were the same number and the objects were headed towards each other, which is why one of them has a negative in my sample numbers. In part B, as long as you use these negatives correctly in your work, you should get the first object that's having a very large negative velocity because it's going to turn around. Meanwhile, the second object was moving towards the left and then ends up moving towards the right after the crash, so its velocity will switch from negative back to positive. Once you do part B and get your correct answers there, part C says that after these objects bounce away from the center of the collision, they will move away from each other and rise back up their respective sides of the half pipe. So initially, GPE turned into KE for each object. Down here, that KE, they're going to have a different amount of KE after the collision, but however much they have is going to turn into GPE as they rise. And what you'll solve for is the height to which they rise. Does that help for right now?
Yeah.
And what else is on your mind? Mine is
Could you go through number 5?
5.
So I got like half of it, but then like the second half of it confused me.
So this is an interesting combination of a collision and also projectile motion. So here we have a collision between a bullet and a block of wood. The wood is initially at rest, so it's going to gain momentum in the collision, and then, now that it has momentum, it has a velocity, it's going to be launched horizontally off of the table. This is again like the old marble cannons where we fired them horizontally and they'd move some distance as they fell. So, in this one, you're told the mass of both objects, you're told the mass of both objects, you are told the height of the table, you're told the horizontal distance the object flies, and you've been asked to work backwards to find the initial speed of the bullet. So what I'd recommend for this is, the first thing you should do is treat this as a projectile motion question. It's just rather than knowing launch speed and finding range, you know range and need to solve for launch speed. You do know the height of the table, and so you could use our old kinematics equation to determine the time it will take the object to fall. That will be the time it is able to, the time in which it moves horizontal distance d, and that will tell you the, you can write this up in hand waving. So, again, like our old projectile motion questions, third equation, vertical analysis will tell you hang time. Hang time can be used to determine what that horizontal launch speed is, the speed at which it launched off the table, such that it moved that far in that amount of time. This then would be the final velocity of the wood and the bullet after they collide in the crash. So once you have this, that would be the final velocity of the two objects combined after the crash. You take that number, you plug it into your momentum analysis, and you'd solve for the bullet's starting speed. The speed at which it would have to collide with the block such that they launch off the table together at this speed. Does that help?
Yeah, me too. Just to make sure, what does it say for like under the two formulas?
Oh, solve for t.
Oh, solve for,
Yeah. Vertical analysis, solve for time. Use that time in the horizontal analysis to solve for horizontal launch speed. Any other thoughts or needs on the homework for right now? Okay. In that case, we're now going to move on to defining our new terms for rotational motion. I'll roll this back up later if you need to see it. As I said Monday, chapter 7 and 8 combined together. We're going to spend the next 2 weeks talking about rotational motion, various variables and aspects that make objects spin versus moving forward in a straight line. And spinning can be kind of weird from a physics perspective, mostly because a lot of people aren't used to thinking about things in the rotational variables that we're going to start using. I find from my students' past experiences and from my own past experiences, a lot of people are used to thinking in terms of straight lines. For that reason, all of the variables that we've talked about so far have been linear variables. Everything we've done up till now in this class could be described as linear, which means of or referring to straight lines. That's why the first 4 letters in linear spell out line. So everything before now has been linear. When I say linear, I'm referring to the stuff we've already done. Linear refers to classic straight line, displacement, velocity, acceleration, and everything tied to them throughout this course. We're now going to begin looking at and comparing rotational variables to those linear ones that we've already covered. And there's a few weird oddities about rotation. Say I take this tire, which I'm going to be commonly referring back to a lot over the coming weeks, and if I roll this object along the ground, so keep an eye on this bracket here. I'm going to move the tire such that it's now on the top instead of on the bottom. We could take a tape measure along the ground and measure the physical distance it moved forwards. That would be the linear displacement of the object. But if we didn't have the ground as a frame of reference, if we could only look at the tire itself, how could we measure the amount by which it moved? How could we measure its rotational displacement? Keeping in mind, I've got my hand on this particular clamp. What's the first thing that comes in your mind on how to describe this rotational motion? Going back and forth between those 2 points. Area of the circle is useful, especially if we could then derive the radius of the circle. That will be very handy later. But we will absolutely need the circle's radius. You are correct. What I'm trying to get at for right now is, notice again the clamp that my hand is on. This is the ending position. and this was its starting position. In terms of just the tire's rotation, how do you describe this amount of motion?
180 degrees.
180 degrees, half of a turn. Does that make sense on like that, where that number came from, the 180 degrees between here and here? That description is the angular rotational counterpart to linear displacement. That 180 degrees describes the rotational displacement of the object. And what we're going to be doing today is describing the various angular variables that describe rotational motion. The word angular just meaning of or referring to angles, rather than linear meaning of or referring to straight lines. So angular stuff means rotation and spinning because you're going through angle measures, rather than linear stuff, which means you're moving some linear distance of meters in a direction. So we're going to begin comparing the linear stuff we've been doing to different variables that describe their angular counterparts. When I was learning these things for myself the first time, I was told to think of the relationship between linear and angular like the relationship between parallel realities in sci-fi or fantasy. All the stuff we've been doing has been in the linear timeline up till now, but now we are crossing over into a parallel world where all the same people are here, but they're all evil and have mustaches. And where everything spins instead of moving forwards. In the angular reality, rather than thinking of displacement as some distance of meters forwards, you think of it as the magnitude to which something spun. As for that reason, the variable for angular displacement is theta, because that's the variable that we use for the number of degrees something turns. Does that make sense so far? So, we took a circle, took it through one complete rotation. One rotation describes the angular displacement of that wheel. It spun one time. That tells you how much it spun. You can further describe that as 360 degrees, which is probably the way most people tend to think about magnitude of rotation. But degrees, 360 degrees, can also be rewritten as 2 pi radians. Depending on what math classes you've had and how recently, radians may be a unit you've used before, and it may possibly be one that you don't much care for. Frankly, I'm not that big a fan of them. But the idea of radians is it's just another unit for angle measure. It's the relationship between radians and degrees is the same as the relationship between feet and meters. It's just a different unit that measures the same thing. And this is the conversion. 2 pi radians is 360 degrees. And the formulas that we're going to begin exploring utilize radians as the unit for angular displacement, and most of the variables here are going to have radians in place of meters. Since instead of distance forwards, we're talking about amount of angle rotated. So, we can describe the motion of this wheel as some number of degrees turned, some number of radians rotated. That is the counterpart to classic linear displacement. The second variable we talked about in this class, as part of the trio currently in the linear column of that graph, of that chart, was velocity. if I roll this thing continuously along the tabletop, we can measure how fast it's moving by clocking the distance it covers in a certain amount of time. Similarly, you could measure how many times it spins in a minute, and that would tell you rotations per minute, which is angular velocity. It's how much did it spin in a certain amount of time, rather than how far forward did it move in a certain amount of time. So linearly, we have the old velocity definition. Velocity is displacement over time. The same formula, the same logic can be used to find angular velocity. This symbol is a lowercase Greek omega, although in practical terms it looks like a weird curly W. It is technically an omega, and so I will probably refer to it as omega on occasion. And this stands for angular velocity. So just like how linear velocity is displacement over time, angular velocity is angular displacement over time. It's exactly the same logic. We're just replacing meters with radians. And this tells you how fast something is spinning, how many radians it covers in 1 second. Similarly though, if you're a car person at all, or if you drive and noticed the RPM meter on the dashboard of an automobile, RPM is another unit for angular velocity. Rotations per minute is basically is almost the same as radians per second. So RPM is another metric for angular velocity. It's just a different unit, like miles per hour compared to meters per second. So they're not equal, but they cover the same thing. I'm feeling so hard. All right. Third variable we ever talked about in this class was acceleration. Acceleration is the rate at which linear velocity changes. And that same logic can apply to the speed at which an object spins. If something is spinning at a certain speed, and then either it speeds up or slows down, you can describe its angular acceleration by how much it sped up or slowed down in a certain amount of time. So linear acceleration is change in velocity over time. Angular acceleration, this is a lowercase alpha, is change in angular velocity over changing time. Same formula, same logic, just new Greek letters and using radians instead of meters. Whereas linear velocity is measured in meters per second squared, angular velocity is going to be radians per second squared. The variable is again lowercase alpha, and this one can be kind of hard to tell the difference between at a moment's glance, largely because when written by a computer in Times New Roman font, there's really not that big a difference. English A has this small vertical stem, whereas Greek alpha has a rightward pointing, slightly more pronounced stem on it. When I'm writing it by hand, I attempt to overemphasize the difference by just not writing the stem at all on A and making it bigger on alpha. But if it really helps you to tell the difference between them, you can overemphasize it even more and make it the Jesus fish. This may actually be where the Jesus fish comes from, alpha and omega and all that. It's either that or literal fishermen. I'm not really sure what the story was there. And if it further helps you remember, you can call these theta, omega, and alpha, or you can call them theta, W, fish. Whatever works in your brain. I will probably use all of the relevant terms interchangeably because they all mean the same thing in my head. And so those are the first three variables in the angular parallel universe. All of the same logic and connective tissue between the linear versions still exists for the angular versions, which is why all of our old linear formulas have angular counterparts. You've probably seen these before, even if only glanced at them, because they're on the top of your formula sheet. The normal Fantastic Four right here, and directly opposite them are the angular Fantastic Four. And that's what these are. It's literally the same as our first four formulas, just replace every variable with its angular counterpart. All of the logic still applies. And even time is still the same between all of them. It's the same t's in between them because time secretly doesn't care about linear or angular, kind of like how time doesn't care if you're in the x or y axis. It's not a vector, it doesn't matter to time. So it's the same t. You don't even have to write it differently. Because all of these connections are the same, we're going to begin by using these variables to just describe some rotational motion in a sample question today and a few samples on Friday as well. And then we'll eventually start describing other rotational concepts utilizing these variables in our explanations. Now, these formulas are the same as the linear ones. So before we move on, I actually do want to show you a couple of new ones because they are useful when doing rotation questions. These three formulas in the middle exist to translate a linear quantity into its angular counterpart and vice versa. If I go back to using this bike tire as an example, this wheel has a specific radius. I could take a tool and physically measure how big it is from the center to the edge of the wheel, and that would be its radius. The radius of a spinning object is what translates its angular data into its linear data. Notice here in the formulas, we've got all the linear stuff equals radius times the angular stuff. So if we were to examine this tire as it spun along the ground, again, I'm going to put my hand on this bracket down here. As this tire rolls and goes through a certain amount of rotation, so 180 degrees or pi radians, it moved a certain distance along the ground. Knowing the radius of the tire lets you use this formula to solve for how far it rolled based on its size and based on the amount it spun. Similarly, if we knew how fast linearly it was rolling forwards and we knew its radius, we could solve for its angular speed. So all three of these just exist to translate linear into angular when those two things are happening at the same time. Because this wheel can move linearly and angularly all at once. The two aren't always separate, they can coexist. One small detail I'll point out about these formulas, because it's a weird note that we inherited from geometrists. That first formula up top, the one in red, says S equals R times theta, rather than D equals or X or Y equals. The reason for that is the formula presented there. Is the arc length, is the same as the geometry formula for arc length. Geometry uses S as the variable for arc length, which is, if you were to take a tape measure and pull it along the surface of a round object, that would be the physical length of a certain section based on how many degrees you were examining. So if I took this wheel and spun it 90 degrees, it would roll a certain distance along the ground, and that distance would correlate to the section of the tire that touched the floor. Geometry uses S for that variable, and so physics has inherited that notation for that reason. But, yep, I even changed it on the formula sheet. Formula sheet says delta X. So, depending on what publication something comes out of, it might use those two, the S or one of the other displacement variables interchangeably. I always get asked about that. I'm going to try to address it now. Questions? All right. So we've got the two parallel realities coexisting, and we have these statements in between that can kind of bridge those two realities. We're going to examine the motion of a car driving forwards, because it has spinning wheels on it, to get a little bit of practice in for these concepts. Here we have a truck. That's actually a truck. Here we have a car driving forwards. We begin with all the old-fashioned linear information that we've always had. We're told car is driving at 29 meters per second forwards initially, before the driver slams on the brakes and begins slowing down at a rate of 1.75 meters per second squared, and will eventually come to a complete stop. So I've noted final velocity as being equal to 0. We're also told the radius of the car tires, which is important. And we've been asked a few pieces of angular information about this scenario, about what the tires are doing as the car slows down. Excuse me. Any questions about the setup? All right. First thing we've been asked for, what is the initial angular speed of the tires, in radians per second? So we want to solve for the initial angular speed of the tires with the information we have. Put the formulas back up on screen. And note, we are hunting for omega initial, W initial. Given what we know, what do you think is our best bet for finding that information?
You change the initial velocity to
Exactly. We know the initial linear speed, and we know the radius of the tires, so we can convert it directly into the angular speed the tires are spinning at. So V equals R times omega. I'm going to be more specific and say V initial equals R times omega initial. 29 equals 0.33 times omega initial. Omega initial should come out to be about 87.88 rad per second, I think. My memory serves. So as long as you know the radius of the wheel, you can directly convert linear information into its angular counterpart. If the tires had a different radius to them, they wouldn't need to spin as many times in order to move the same distance. If a bigger wheel is spinning at the same speed, it covers more distance. It's one reason why monster trucks are kind of absurd. A smaller tire has to spin faster, spin more times in order to cover the same distance. So this is initial angular speed in radians per second. For the sake of practice, we're going to convert that additionally into the other unit of RPM. This is the unit that your car tends to display. It's usually on the left side, opposite usually speedometer's in the middle, gas is over here, RPM is somewhere over here. I don't tend to pay much attention to it because while I like cars, I'm not a gearhead. So we're just going to convert this into RPM. We're in rad per second, and we want to turn that into rotations per minute. So radians needs to convert to rotations, seconds needs to convert to minutes. Seconds to minutes, we've just got 60 seconds to 1 minute. Since seconds starts on the bottom, we'll put 60 on the top to cancel out seconds and leave minutes on the bottom. Then we need to address how to turn radians into rotations. When in doubt, remember this statement. 2 pi radians is 360 degrees. 360 degrees is 1 full rotation. So 2 pi radians is 1 full rotation. So that's the conversion. 2 pi rad equals 1 full rot. And I believe that answer should come out to be about 840 approximately. If that feels like a big number, remember it's rotations per minute. And this car does start at a pretty fast speed, and most cars' RPM gauges go up to about 10,000 RPM. So it's not that bad. A couple of questions will have you converting into and out of RPM. Main thing to remember is just that it is an alternative unit for angular velocity, and you can convert it into and out of radians per second like this. Any questions on the first one? All right. Then let's quickly get through the second part here. How many radians does each tire rotate through before the car stops? The car is going to come to a complete stop. We want to know what theta is as it does so. I'll put the formulas back up on the screen. And there's actually a couple different ways we could go about this. Since we know the car's the radius of the tires, we could either solve all of the linear data, solve for the distance the car drives forward as it slows down, which would be the delta x in one of these formulas, and then convert it into its angular form. Or alternatively, we could just work one of the angular formulas, converting things from linear into angular as needed, and solve for theta that way. Either option works, it's just a question of which end do you want to do the conversions on. We've already converted most everything we need, so I'm in favor of the angular option here. Oops, that's not right. We've already found angular initial velocity. Final angular velocity is just going to be 0, because if initial linear speed is 0, final linear speed will also be 0. So, wait. I said that all wrong. I apologize. Final linear velocity is 0. Plug in a 0 for velocity, you'll get a 0 for angular velocity. So, final angular velocity will also be 0. That is what I'm trying to say. So we've got most of the linear stuff converted already. If we want to solve for theta, the formula that I'd actually recommend is angular formula 4. We know initial and final velocity. We want theta, so all we would need is angular acceleration. I want to go ahead and mention the one reason we're not using this one is because this inherits the restriction that its linear counterpart has. Linear Formula 1 doesn't work if you're accelerating. Don't you put that asterisk in your notes. Angular Formula 1 has the same limit. So that's one reason why we're not using it here. I'm choosing angular number 4. If you wanted to work in the linear space, you could use linear number 4 and then convert delta x into theta. That works too. All we need to do here, though, is convert a into alpha. And that conversion factor looks a lot like the velocity one. Linear equals radius times angular. Therefore, angular acceleration would be k over r, negative 1.75 over 0.33, and that's negative 5.3 rad per second squared. So that would be what goes in for alpha. Final answer, I think, comes out to about 729 radians. Questions right now? Now, rotational stuff is weird. It's all right if this feels weird or it doesn't quite make a lot of sense yet, because out of all the parts of this class of 1500, I feel this is the strangest part. This is the part that takes some time to wrap one's head around. So if it's taking time, that is okay. We've got 2 weeks to talk about it. That's why we're spending a full 2 weeks on just rotating things. For right now, main thing for tonight is chapter 6 homework. So focus on momentum for tonight. On Friday, we'll revisit this, work more examples, and start tying it in, using these to describe various other angular processes. Questions before we break for today? All right, let me know what questions you guys have or what you guys need as you finish up the homework tonight, and have a wonderful day.